Okay, all right. Well, welcome back. Happy Thursday. So today we kind of will continue talking about the different security topics, and in particular, we'll talk about crosstalk and fault injection in NISQ quantum computers. So as you'll see, some of this it's relatively older compared to what we've talked about some last lectures, but it was sort of some of the first work that was done on security and of quantum computers was really about crosstalk and different fault injection. So, okay, to maybe review with our favorite picture, we talked about side channels in controllers 2 lectures or so ago, and then last time we talked about fingerprinting QPUs, which is a little bit like sort of side channels trying to figure out which QPU is being used or which qubits are being used. I mentioned very briefly about possibility to fingerprint some of the other components in the quantum computer, although that might be I don't know, more overlap with the classical security, and then yes, so really the focus was on the fingerprinting, just the QPUs, but again, using like the DRAM paths for the GPUs and high performance computing that's attached to the quantum computers might be something interesting. So definitely some interesting ideas, but maybe not so quantum specific. So today we'll focus on crosstalk and fault injection in QPUs, which is basically about how do you disturb the execution of quantum circuits to usually cause them to give you incorrect outputs. And then looking at the picture again, you could also have fault injection in some of these other components. But again, maybe this is sort of too much overlap with classical security. So we'll really focus on the fault injection in the QPUs. And the main setup for the crosstalk and for the fault injection is kind of either in single tenant or multi-tenant. So I think we looked at this picture before. So whenever you're using a quantum computer, either you can have like a single tenant setting where just one user runs, then you have reset the qubits and another user runs and so forth, or you could have a multi-tenant setting where multiple users are running sort of in parallel to each other. And in this multi-tenant scenario, the crosstalk typically means one user trying to interfere with another user who's running in parallel. So you do have to have multiple users or multiple circuits executing concurrently on different qubits. And then you also need to have this multi-tenant setup that you can have multiple users on the same machine. Now, even if you don't have multi-tenancy, it's still possible to look at fault injection or sort of not exactly crosstalk, but causing problems if one user who's running on the qubits somehow able to affect the qubits and attack the other user. So these are sort of the main scenarios for the existing work on crosstalk and fault injection. And then again, no quantum computer provider offers multi-tenancy today. So this is not exactly a practical security attack, but it like sort of a lot of times we make some simplifying assumptions to understand the security, and in this case the simplifying assumptions are about sort of being able to have multiple users running concurrently. So especially now with a 100 qubit machine, it might not be practical to share it, but if you have thousands or hundreds of thousands of qubits, then multi-tenancy might become practical, and then we have to kind of consider these issues. And then part of the work on crosstalk and fault injection sort of involves the single tenant, but then in the single tenant, there are sort of again 2 ways of actually executing the single tenancy. So in a classical computer, you just run your program and then that's it. But for NISQ quantum circuits, you have to execute them multiple times, and so each time we execute the circuit, it's called a shot. So you could think of a scenario where all the shots of one user are here on the top. All the shots of one user are executed together. Shot 0, 1, 2, 3 until n, and then the new user starts, and the shot 0, 1, 2, 3, 4, so forth. So all the shots of each user would be grouped, and then we could call that like a batch execution. And another option is to possibly interleave the shots of different users. So you might have user A shot one, then user B shot one, then user A shot one, user B shot one, then user A shot two, user B shot two, and so forth. So you could interleave. And for the security, considerations, we can consider both of them. So either, some fault injection might be happening when the shots of the different users are alternating, or between the batches. Now again, as far as we know, no cloud computer provider interleaves the shots of different users today. So again, so it's kind of less practical attacks, but maybe more powerful, because if the users are interleaved, then you could be causing some fault between each shot. So if a user has like 1,000 shots of their circuit, then you could basically inject that fault 1,000 times. If you just have the batch execution, then you effectively get to do fault injection once, which is when the users switch, and then if you affect one shot of 1,000 shots, basically, the results of all the other shots will sort of self-correct for any faults. But as we move to fault-tolerant quantum computers, on one hand, fault-tolerant quantum computers should take care of some of the faults and errors, but they also might reduce the number of shots that you have required. So then maybe even injecting one fault might be more problematic. So this is kind of the setup for the crosstalk and the fault injection, either between users if they're running parallel, or among the users if they're running sequentially. And so a lot of the crosstalk and fault injection work has been prototyped on IBM. I think mostly because IBM used to give a lot of access to the machines. So this is some examples. Most of the examples today are from IBM machines, but it should apply equally to other type of machines. But one specific thing to superconducting machines, which IBM is a type of superconducting architecture, is that you have I've seen this topology again a few times now. You have the fixed topology with different qubits, and then each line sort of represents the coupling. So whenever you want to execute a 2-qubit gate, you have to have a coupling between the qubits. And we'll talk about later about swap gates. So if 2 qubits aren't, if you want to do computation between qubit 108 and 126, since they're not adjacent, you have to do some swapping to swap the quantum states together. So we'll talk about swap and actually some security issues with swaps a little bit later, but this is kind of the setup for if you're using a superconducting quantum computer. You have the qubits and the fixed couplings, and then if you have a single tenant setting, then the user gets all the qubits and then does their work, and then they all get reset, and then the next user runs. And then if a user there's multi-tenancy, then the user will get one user will get some of the qubits, another user will get some other qubits, and then sort of they will execute sort of on separate parts of the quantum computer. But these couplings still remain because they're fabricated. You cannot remove them if you even if there are multiple users on the machine. So for fixed topologies like this, when you have multi-tenancy, you still have to, the couplings that are there that are not used. And some of the early work that looked at security of quantum computers and crosstalk actually abused the fact that you have these fixed couplings that are there no matter what, even if you have two users that are separate. So this is actually a picture topology of a recent IBM machine with 127 qubits. When people started looking at crosstalk and fault injection, we still had like a 5 or 7 qubit machine. So this on the top is a I guess 2021. So around early 2000s, this is a topology of what used to be I guess a 5-qubit quantum computer from IBM. And the idea is the same. You had the couplings connecting the different qubits, but since there are so few qubits, we didn't have this nice heavy hex topology just yet. It was just a 5 qubits. But the main idea, even a few years ago, when people were exploring crosstalk, is that basically what happens if you divide up the machine into multiple users, and in particular, let's say you have a few qubits that you assign to one user. Let's say they're doing some I don't know, quantum pattern. They're just doing some computation, and then you assign a few other qubits to a different user. And then now, like I mentioned, even if you assign different users to different sets of qubits, let's say there's this one coupling that physically remains there, and then there's no way to turn it off or disable it. It stays idle, but it's still physically there. And basically, what was experimentally shown is that if you have few qubits and you execute some sort of a quote malicious circuit on it, it can create a lot of noise and crosstalk that will affect the other qubits. And I'll mention in a slide or two that like a malicious circuit, for example, can have a lot of CNOT gates, which seem to generate a lot of noise, and it could affect the victim circuit. So in all the crosstalk setups, you have one sort of quote malicious circuit that's trying to disrupt another circuit that's running on the same quantum computer at the same time. And this is just a different way of showing it, that again, if you have multiple qubits, some of them are sort of the victim, and then the attacker tries to generate a lot of noise or some disturbances that basically affect the computation of the victim. So as an example, since a few years ago we only had few qubits to work with. A lot of the examples are like a 2 or 3 qubit circuit. So like a 2 qubit Grover circuit could be assigned to 2 of the qubits, and then the attacker could be this circuit, which has, let's say, bunch of CNOT gates. And the idea is that when the circuit executes, it generates outputs with certain probabilities, and then when you have an attacker circuit, can you change the output probabilities or sort of lower the output, the correct output of the circuit. So I think in most of the cases, the results have been that you're sort of able to mess up the computation. You're not. I don't think anybody has been able to sort of really drive the computation to a specific state, which would be really, really cool. So I think that's maybe some future things, is to not just mess up the computation, but actually get some predictable output too, which would give you more sort of control over the victim. So yeah, so that's the setup. And now if you, for example, so experimentally, circuits like bunch of CNOT gates seem to generate a lot of noise. So I think so this obviously does no computations, bunch of CNOT gates together, but because CNOT gates usually much longer, maybe execution times like something like 10 times longer than a single qubit gates. The control pulses that drive CNOT gates, will have consequently much bigger power. So kind of all these different effects somehow make a bunch of CNOT gates an interesting circuit that can sort of doesn't do any practical computation, but disrupts the system. I mean, you could think of it like on your computer. Maybe you could run a bunch of multiplications that aren't actually useful, but it just heat up the computer because the multiplier consumes a lot of power. So just kind of nonsense circuits that just mess up the operation of the system. As an aside, one interesting thing, if you do some weird circuits like that, like for example, a bunch of CNOT gates, the compiler might try to actually optimize it out. So none of the so far none of the quantum computing software really offers any antivirus or security features, but it does a lot of optimization. And if you give it like a sort of a nonsense circuit like a bunch of CNOT gates, it will realize that this is not doing anything useful, and it will maybe eliminate the CNOT gates and sort of optimize away. And then so if you optimize this away, then you no longer can generate a lot of noise. So but there's some tricks, like for example, you can insert some small delays or some interleave the CNOT gates with other small gates just to prevent the compiler from optimizing things away. So in the end, you might have like a Grover circuit and this attacker circuit with bunch of CNOT gates, and then like I mentioned, that the goal is to mess up the output probability. So for each quantum circuit, we remember, we at the end we measure the qubits to collapse to the binary states, and then for let's say for a two qubit Grover without some interference, let's say this would be the output. So then the state 1 would be the main state, and then the other states would be much lower. So since we have two qubits, there are 4 possible combinations for the output. So 0 0 0 1 1 0 and 1 1. And then after you run it, this multiple shots, 500, 1,000 shots, you figure out which is the dominant state, and that corresponds to your solution. So without interference, let's say this is a dominant solution, maybe almost 83% probability for that state. So you choose that as your so that would be sort of the output or the solution of the Grover search. Now, if you have like an attack, you can see that you can drop it by almost 30% by basically creating interference, and you can see that this goes down, some other states go up. So basically, you're sort of messing up the output of the user circuit. So in this case, you sort of 1 1 is still the correct solution, but it's much more noisy. So if somebody can create even more noise, maybe they actually flip the solution. And this actually used to work for different algorithms. I think, and I mentioned actually one of the intro lectures about the Deutsch-Josa or Bernstein-Vazirani, some of these algorithms developed many years ago. So now people can actually run them on a few qubits. And again, you can see that with by creating some noise, you drop the probabilities. And in one case for the Bernstein-Vazirani, almost 0 1 was the dominant state, and now almost 0 0 becomes the dominant state. So it's very, very dependent on the circuit and on the machine and everything. But the main takeaway is that if you can have if you can have sort of one user running next to another one, they can try to generate a lot of noise to mess up your computation. And you can try many different type of attacker circuits. This is just from this one paper, but CNOT gates or interleave the CNOT gates with some other gates so the compiler doesn't remove them, or flip the direction, or have some patterns. As the machine gets bigger, you can use more qubits for the attacker, so you have more CNOT gates, and then sort of in the end, the more CNOT gates you can fit in, the more noise you can create, and that becomes more of a issue with the disruption of the victim. So people explored this idea of crosstalk when one circuit affects adjacent circuit. Some other work more recently, people have looked at sort of how do you improve the crosstalk. So for example, there's some work that looks what happens if you actually generate the crosstalk. If the attacker and the victim can be physically on 2 sides of the victim. So this is actually sort of abusing the IBM topology, where you can see that, let's say there's a qubit, and then it's because of the topology, it's sort of sandwiched between other sets of qubits. So if you take that qubit as a victim, then you could run some computation, again, a bunch of CNOT gates on the other qubits, and see if you can affect the state of the qubit. So here the now okay since so since the victim is just one qubit, of course it can't really do any computation, but you can still look at how the state how the crosstalk might affect the state of the qubit, and then basically the sort of some takeaway from this work is that by running a bunch of CNOT gates on both sides of the victim, they actually can flip the state of the qubit from 0 to a 1. So normally you initialize the qubit in the ground state, and then by itself it shouldn't enter a higher energy state. So the only way to explain this kind of flipping from 0 to a 1 is crosstalk and interference from these adjacent qubits. And they also kind of show that you can flip the qubit from 1 to a 0, which the crosstalk accelerates, but also the qubit can naturally decay to 0. So if you want to demonstrate that this one qubit actually is being affected, you want to show that it flips from a 0 to a 1. And there's some some limitations, like they need to do like 40,000 CNOT gates to actually flip the qubits, which is quite a bit. So but as a demonstration, kind of shows the idea of putting the attacker on two sides increases the chance of flipping the qubits. And some other work to give you ideas how people are kind of becoming more clever. So this is again part of the IBM topology, but what here so in the previous sort of like in the previous pictures, it kind of implied that the attacker and victim need to be adjacent, so they can share like some coupling to create the crosstalk. But some more recent work actually looked at are there some couplings between qubits which are farther apart, and here kind of pretty cool. These red arrows basically show that let's say if you execute a CNOT gate between qubits 21 and 23, that somehow has effect on the qubits 24 and 25. So although the qubits and the couplings are not adjacent in the topology, in the logical diagram in this graph, maybe through the layout of the qubits or the chip, there's actually some effect. And a lot of this work, as you can see, they doesn't really explain the reason for the actual qubits flipping, and part of it is that, for example, like for IBM, we don't know the physical layout or really the structure. So all that you have access to is you have the machine, you can run some circuits, and then observe the results and see if you see some unusual changes in the output or bit flips. So that's sort of kind of not satisfactory because there's not a clear answer, but at least it's experimentally observed that through either the layout or the substrate, there's some coupling between these gates or couplings that are not adjacent. And if you do something on 8 and 9, that actually affects 19 and 20. So the users, here's the picture. So now the victim and the attacker actually don't have to be next to each other, but they can be located some distance away. So that's I didn't mention here, but at some point people propose that if you isolate, maybe it's on the next slide. Yeah. So after the initial crosstalk was proposed, people then proposed, okay, let's put the circuits farther apart and keep some idle distance like here that might prevent the attacks. But then, for example, this work showed that doesn't work. Like even if you have, the victim is isolated to the attacker by having some idle qubits, that doesn't actually help. I think like with everything in security, it's sort of like a cat and mouse game. You find something, somebody has a defense, you find it again. So now you don't have to be adjacent to the victim. You can be a little bit away. And I'll come back to this picture of the attacker. But again, the attacker is again a bunch of CNOT gates, and they're able to sort of again change the output probabilities of the circuit. And I'll come back to this in 2 or 3 slides. Oh yeah, sorry, actually here. So what I wanted to kind of discuss is that we mentioned that one way of bypassing the compiler is to insert some minor delays or single qubit gates to kind of prevent the compiler from eliminating this circuit. But it doesn't really if I don't know if you look at the circuit, or maybe nowadays if you use some machine learning algorithm, you can sort of figure out that it's still basically a bunch of CNOT gates, which is not a practical circuit, and it might be easy to identify that this is malicious circuit. So what this paper that we just talked about basically proposed is that in the attack circuits, you use a lot of CNOT gates, and there's a interesting observation that another circuit that uses a lot of CNOT gates in like this grid pattern is a QAOA. It's one of the variational circuits. So actually, if the attacker just runs a QAOA circuit with a bunch of CNOT gates, it's sort of hard to how to say it. You cannot accuse them of having some malicious circuit, because this looks like a reasonable QAOA circuit. So the attacker can sort of hide or obfuscate their malicious code by pretending to be this type of a circuit. So the attackers first have to bypass some restrictions of the compiler, and then make it sort of less obvious that is that's a malicious circuit, so they can actually execute. So this is sort of how people have also been trying to hide the circuits, or kind of demonstrate that this is more realistic and not just something very easy to find out. So sometimes you have to think like an attacker to see what is a malicious circuit. Okay, so we'll talk about two more types of sort of crosstalk and fault injection. I think the standard crosstalk attacks are about executing a circuit and causing some problems on adjacent qubits. One of the other types of attacks is similar, but deals with basically abusing the idea that the different qubits have different frequencies, and that they have sort of unique control poles. So I guess we haven't talked about it in this class very much, but for like a superconducting architectures, each qubit is a transmon. It's a circuit that you fabricate, and each qubit has a sort of unique frequency, and the frequencies are designed to sort of be unique, so that they minimize the interference when you're sending signals to the different qubits. And this is just a random table from IBM showing that for different qubits, 1, 0, 1, 2, 3, 4, there you can see the frequencies are 4.6 gigahertz, 4.7, 4.68. They're all slightly different on purpose. But an interesting way to kind of abuse that is basically by trying to kind of think, what if you send the wrong pulse on the wrong qubit? So again, the idea is that each qubit has its own frequency. So if you send a control pulse to a qubit that's with a wrong frequency, that shouldn't do much, shouldn't work on that qubit. Doesn't make sense. But we're not trying to make sense. We're trying to kind of abuse the system. So the idea is, what if you take a pulse that's designed for, let's say, for qubit 0, and then you execute it on some other qubit, like qubit 75. So so this assumes you might have access to pulse level control to define your own custom pulses. But if you can do that, then you might be able to create a pulse on your own attacker's qubit that actually has the frequency matching the qubit of the of the victim. Yeah, so pulse on qubit 75 should have no effect if it has the frequency of qubit 0. But sort of an interesting observation is that what happens if you take one or more of these pulses that are at the frequency of qubit 0 and you execute it somewhere else on the machine. And then so experimentally, it's a very interesting result that if an attacker who is farther away on the chip executes a bunch of control pulses at the sort of quote wrong frequency, so these pulses are not going to do anything useful on the attacker's qubits, but somehow through crosstalk or some coupling within the substrate, this actually ends up affecting the qubit 0. And here you can see that for the different target qubits, again they're initialized in 0 state, so they shouldn't kind of automatic, they should not flip to a higher energy state unless there's some crosstalk or interference. And then here with 20, so you have like 30, if you have 30 or more different qubits that are executing this wrong control pulse, you can actually change the output from mostly ones, from mostly zeros to mostly ones. So the attacker who is far away can basically flip the qubits. And so again, the mechanism is not clear, but experimentally you can observe this result. Now this assumes access to post-level control, which now different quantum computer providers are sort of disabling. So this would be sort of difficult to replicate now, but it's an interesting idea of what if you have low-level control to send wrong pulses to your qubits, that might actually affect the long-distance victim. So this was sort of slightly different from the typical crosstalk because you're using custom control pulses, but still the same idea. Okay, so another sort of topic about the sort of related to crosstalk and then maybe more fault injection is about these stealthy swap gates. So I think I already mentioned that if the qubits, if you're trying to do some computation between qubits that are not adjacent, you have to insert this swap gate. So in this example, C naught on qubit 1 and 2 is possible because 1 and 2 are adjacent in topology, but C naught on 1 and 3 is not because they're not adjacent. And then so what you need to do is you need to put in a swap gate to swap the state. You're not moving the qubits, but you're swapping the state of the two qubits so that the state of qubit 3 moves to qubit 2, and then you can execute the C naught gate. So when you have swap gates, so actually they can be realized as three C naught gates. So this is a typical symbol for a swap gate, and it's equivalent. You can just kind of remember that it's equivalent to three C naught gates. So basically, you perform C naught operations between, let's say, qubits 2 and 3 times to get the state of qubit 3 to move to 2 and 2 to move to 1. And then so the way that the swap gate works, again, you have three C naught gates, and then the idea for the C naught gate, for the control NOT gate, is that basically if the control qubit is 1, then you flip the target qubit. Otherwise you don't flip it. And of course, if the control qubit is in the superposition, then you both do and do not flip the target qubit. So it's kind of, it works with all the quantum states. But for the swap gate, let's say you have some 2 qubits with initial state A and B, and then you can kind of write it out like this: that when you apply the first gate, so A is the control in this case. So if you apply C naught to A and B, then A is unchanged, and then B will be flipped if A is 1, so like kind of like an XOR operation. And then the next time you apply the CNOT gate, the control and the target are flipped. So for the second CNOT gate now, A XOR B is the control, and then the original A is the target. So after you apply the CNOT gate, the A XOR B remains as control, and then the target, you're effectively sort of can visualize it as again XORing A with A XOR B, but A XORed with itself is just this, so you can end up with A XOR B and B. And then for the third CNOT, you flip it again. So now you have B and then A XOR B, and then B stays the same, and then now the B's cancel out, so you end up with B and A. So by executing three CNOT gates in sequence, you basically swap the state of the two qubits. So that's how the swap gate works. And okay, why are we talking about the swap gate? So we'll get into the actual fault injection attack in a slide. But the main idea is that the swap gate is necessary to move the qubits around, but it incurs some overhead of 3 CNOT gates, and especially if the CNOT gate, let's say, is 99.5 or it's not perfect in its fidelity. So then CNOT gate basically is 3 times that. So the fidelity of swap is basically decreases the fidelity of the circuit because you're inserting a lot of CNOT operations. So if somebody is able to insert a bunch of CNOT gates into a circuit, or force the circuit to have a lot of CNOT gates, it will naturally degrade the performance. So this was a work from 3 years ago now. So they had a clever idea of, if you're able to force the circuit to somehow have more CNOT gates, that will degrade the quality of the circuit, which is sort of like a fault type attack where you make execution much worse. So this is actually a nice diagram. Again, actually using the same old 5-qubit IBM machine, but here, let's say in the first case, let's say the attacker is assigned qubit 4. So then, if there's this circuit that's executing on qubits 0, 1, 2, 3, this is the circuit. So you have a CNOT gate between 1 and 2 that can execute. You have a CNOT gate between 2 and 3 that can execute. Then again, 1 and 2, and I think there's a mistake in their diagram. So eventually, to get 3 and 4, you have to insert actually one swap gate, which actually should be between 2 and 4. So before you can execute the CNOT gate between C and qubit 3 and qubit 4, since there's no coupling here, you have to swap. Let's say 4 and 2 should be swapped, and then 3 and 4 can execute. And then if you already swapped 4 to be here, then you can see then the 1 and 4 can execute. So a little bit convoluted. I think there's a mistake in that picture. So but the key part is that to execute this victim program with this assignment, you need to add one CNOT gate, one swap gate to move the qubit 4 around. And then so in the malicious case, so now if the attacker somehow is able to force themselves onto qubit 2, so that if the attacker is here, then the victim has to use, let's say, these 4 qubits, and if you go through the circuit again, you have 1 and 2, you have 2 and 3, 1 and 2, but now you have to insert more extra gates to actually complete the so 3 and 4 can execute in 1, but then to get 1 and 4, then 4 has to be swapped once and then swapped again. So the case 2, the malicious case, you basically by occupying qubit 2, you're forcing the victim to have one extra swap. And then any extra swap will degrade the performance of the victim. So this is a little a little convoluted setup to be able to force yourself onto specific qubits, but in their proposal, the idea was that again, if the adversary is somehow able to manipulate the scheduling algorithm of the quantum computer, maybe they could get their their quantum circuit onto specific qubits, which would disrupt the victim. And this is just a kind of a nice picture just to show that compared to some, let's say, if a victim is given a few qubits, if that topology is disrupted by the attacker, so if you end up, instead of doing this configuration 5, if you're forced to use some other qubits because users are or the attacker is already occupying them, that you can see that, in the worst case, you can have bunch, 50%, let's say, yeah, up to 50% more CNOT gates, and 10 or more swaps. So that can actually degrade the performance of the circuits quite badly. And it's not mentioned here, but this can be combined with another idea that in addition to inserting the swap gates, which degrade the fidelity, certain qubits within the topology are slightly worse than the others. So if you look at the fidelity of the qubits in like an IBM machine, different qubits have different fidelity. So if the attacker is not just pushing the victim to use more swap gates, but maybe qubit 0 has bad fidelity, and then you force the victim to use qubit 0 because you're already occupying qubit 5, then there's an added problem that the victim is using worst qubits and has bunch of these CNOT gates. So if again, if the attacker is able to get themselves located on a specific part of a quantum computer, then they could kind of execute an attack like this. So this is not a crosstalk anymore, but having more swaps creates more noise, which is kind of similar to a fault injection attack. So any questions about these attacks, fault injections, and crosstalk? So I think that maybe some summaries that a lot of sort of crosstalk attacks have been explored since about 2020. Initially they mostly focus on if you run some weird circuit on some qubits, how it affects adjacent qubits. But now people are looking at these custom pulses or injecting the swap gates, kind of more weird operations. And I think like I mentioned, there's no multi-tenancy, so most of these crosstalk attacks are sort of experiments. I mean, simulated on real machines, but still not a real attack. But as the machines get bigger, they might become an issue. Or there's a sort of a development in lately that most of the quantum computers are sort of moving to an architecture. I don't know how many of you've heard about chiplets in classical computers. Maybe, yeah. So in a classical computer nowadays, the processor actually might be made of different chiplets. So you have like a processor, that you have a high bandwidth memory on top of it. So there's actually many chips put together. And then it's the same idea for quantum computers, that you might have a bunch of smaller chips that are interconnected together to make a bigger machine. And one interesting scenario might be that while the users might not have multi-tenancy, maybe each user will get a chiplet, or the granularity of the assignment will be a multiple of a chiplet. So if there's some crosstalk between the chiplets, that might be another kind of interesting thing in the future. So I think on one hand, lots of attacks on crosstalk. On the other hand, a little bit unclear, when multi-tenancy will be available and in what form, which would sort of determine how these attacks might translate in practice. Okay, all right. So the next few slides, just wanted to talk about another type of fault injection attack. This one is dealing about the reset gate. So it's no longer crosstalk, but it is a type of a fault injection. And the main idea is that if you can, actually both in multi-tenant or single-tenant scenario, at some point the users switch and then the qubits are reset, and then another user runs. So if you're able to sort of affect the reset gate, that the user B could sort of do a fault injection attack, where they could kind of disrupt the operation of user C if they can mess up the reset or make sure the reset doesn't work correctly, or control the initial state of the qubits after the reset. And it actually applies to both single tenant and multi-tenant. But just as an aside, so what is a reset gate? So again, so in quantum computers, you can't reset the qubits, or you can just write like a 0 into a qubits. So really the two ways to reset the qubit is, one, to either basically let the qubit idle for a long time, so they lose their state. We mentioned the T1 and T2 times, decoherence and dephasing time. So if you just leave the qubits alone, they will naturally lose their state and sort of reset themselves. But this takes some time, on order of microseconds or milliseconds. So a lot of quantum computers now support this active reset, which basically is the idea that you measure the qubit. So the measurement is a non-unitary operation. You just collapse the state of the qubit, but then if you measure and you end up in a 1 state, then you actually have to flip it back to a 0 state. So there's an assumption pretty much always that when a user starts or when a circuit starts, all the qubits are in a 0 state. So if you measure the qubit and it ends up in a 1 state, then you have to flip it to a 0 state to make sure the qubit is in a 0 state. So having like an active reset speeds up the time that it takes to reset the qubit. So it's promising, but it might have some problems. So again, kind of in a picture form, basically the idea is if the qubit is in different states, then after the reset, qubit should always end up in the 0 state. But actually, due to some problems with either the measurement or the X gate not being perfect, then the actual final state of the qubit might not always be 0. So if you can somehow manipulate or control the state of the qubit before it resets, then the reset might not work, and then you end up with something other than a 0 state, which is basically like the initial state of the next circuit will be imperfect, and it's like a fault that you inject, right? So if the qubits are not 0 when the user starts running, it's a faulty input sort of, and then that propagates through the circuit. So again, this could be either a single tenant, multi-tenant. If you can disrupt the reset gate, then you can affect the next user. So this is actually based on some. So the specific attack. Okay, so how do you disrupt the reset gate? And then so one of the specific attacks was kind of abusing this idea that a qubit has only two possible states. So we mentioned that throughout this course we sort of focus on qubits, which are either ground state or excited energy state. So there's sort of two states, quantum mechanical system. But actually, in practice, you can have many different levels. So the transmons could be excited to higher energy levels beyond the two, and then that is actually the basis of the attack. Like the whole quantum computer works on is calibrated or designed under the assumption that the qubits will only be in one of these two states. But then what happens if you could get out of those states? So a key idea, I'll not go into details here, but basically if you can design a custom gate that sort of excites the qubits into a higher energy state, then you can basically get out of beyond the zero and one state. So we actually already saw the X gate, or the NOT gate is basically like a gate that goes from 0 to 1 or 1 to a 0. But you can design other gates. They're usually called pi gates. There, where as you can see, if you have some pi gate between two energy levels G and E, then if you apply a pi gate to some qubit, then it effectively swaps the states of the amplitudes of the two states. So it can be used to sort of go from 0 to 1 and 1 to 2 and 2 to 3, and sort of similar to the work that I talked about, the custom control pulses being used for sending wrong frequencies to wrong qubits. This does require you to have custom control pulses to design these other gates as well. So there's some extra access that you need, but if you have that access, you can create these new gates to get the qubits into a higher energy level. Yeah, question.
You just answered.
Yes. Oh, okay. Oh, yeah. So you need, so these gates are not natively supported unless you have some extra access. But this is so for example, like I mentioned at some point, we have qubits, you have qubits. So with qubits, you work with 3 energy levels. So if your machine is designed for qubits, then it already supports 3 energy levels. So there are positive uses of supporting or having more than just two levels. But the question is, can the user have the access to actually go beyond what's allowed? And in a way, you can think of it as like you're finding a way to go beyond the abstraction of the 2 levels, and you get into the higher energy level. And so you get the qubit into a higher energy level, and then the idea would be like this. There, you set the qubit to a higher energy state, and then when it's being reset, then perhaps the reset is not going to work correctly because it wasn't designed to handle it. And that's indeed what the work found out, is that if somebody's able to set the qubit to a higher energy level, then you reset it, and then you run the victim. Actually, that reset doesn't work. So the initial state of the qubit is actually not 0. And this is kind of a nice picture from the research work that just showing what's the state of the qubit, and then let's say how many resets were applied, and then just showing that for different qubits within the IBM machine, kind of what was the effect, and then here's the probability of 0. That means what's the probability of qubit being in the 0 state. And okay, so if the qubit is in the gray line, the qubit is in 0 state, then of course the probability is almost 100%. If the qubit is in 1 state, then if you don't reset it, the probability of 0 is 0. But when you reset it, it usually goes back up to 1. So resetting works for the first energy level. but then this blue and red line show that if you try to reset if you put a qubit into second or third energy level and then you apply the reset gate, it actually doesn't work very well. It doesn't get the qubit into the ground state. So that means when the victim executes, that initially, instead of things being in zero, they're in some other state, which effectively messes up their computation. And then just to wrap up, this kind of a demonstration that that if you have you can look at the reset column here. That's the one. So actually default, this is if you let the qubits idle and just naturally lose their state, then no matter the energy level, it loses its state, so everything works. But if you look at the reset column for different algorithms, if the qubits is in 0 and 1 state and then you reset them, the reset works correctly. So the Deutsch-Jozsa or inverse quantum Fourier transform or this Grover search, the brown and the green, so that they give you the correct output. So the probability of the correct output is pretty high. But if you have the qubits in 2 and 3 state, then the reset doesn't work, which means when the Deutsch-Jozsa executes, the initial state of the qubits is not correct, and then so predictably the ability of getting the correct output of the circuit is much less. So it's a very assuming you have the post level access control to have these custom pulses, it's a very nice fault injection attack where you inject sort of the fault into the initial state of the qubits, and then in these cases you totally mess up the computation of the victim. Questions?
So the reset of the operation you're applying, or is it just like the exponential decay? Or is it waiting for it to go back?
So good question. So the reset, right? So the reset is a custom, and we call the reset gate, but it's an operation. So it's explicitly applied to the so you do a measurement and then you flip the qubit if it's 1. So it's explicit operation. The exponential decay, that's the thermalization. So if you let it wait for some milliseconds, everything decays anyway. So again, it's actually here like the default. This should show the thermalization. This is the exponential decay. If you just let everything decay, then no matter what, the qubit goes into 0 state, and then the circuit executes correctly. Yeah.
Is it possible to design a reset gate that can handle the higher energy states?
Yes. Actually, there's one slide about it about a cascading secure reset. But yes, if you assume there will be a higher energy state, you can design a gate. And then the basic problem here was that the reset just didn't assume those possibility of those higher energy states, and that's why it didn't work. But you can totally design them. Yeah. Question. Okay. Yeah. So this is kind of an interesting, basically an interesting mismatch that on one hand, the reset gate or the other gates work with just 0 and 1 states. On the other, the user is able to put the system into a higher state. So then that creates a problem. And actually, I had one slide answering that question. So actually, you can, the CSR is actually a new type of a reset gate that can deal with this problem, is where it's actually, so the reset gate only works with 0 and 1, but then we also talked about this pi gates that can switch between the different energy levels. So if you combine the two together, you could have this design where so here the lines are actually the energy levels. They're not qubits, but they're just energy levels. So let's assume you support up to four energy levels. So the reset gate could reset the first energy level, but there could be still something at the higher energy level. So then you could apply the pi gates to sort of swap swap the whatever's at the higher energy levels to kind of go down. Then you apply the reset gate again, and then you apply a swap gate and apply a reset gate again. So it's sort of you reset whatever's at the first energy level, and then you apply a sequence of high gates to bring other things down, knowing that this is for sure zero now. Again, you reset again whatever was at zero, and then you bring more things down, and kind of so if you have 4 levels, then you need a sequence of 3 resets. If you have 5 levels, you need you can just extend the sequence to however many levels you're supporting. So not all the research is about attacks. It's also about defenses, such as designing these secure reset gates, or thinking how to isolate the circuits from the crosstalk. So actually, this pretty much wraps up for today. So in terms of crosstalk and fault injection, there's this work on the reset gates, sort of abusing the reset gates to inject the faults, and then most of the other work here was on the crosstalk among the qubits. So within the QPU, you really have either among the users, if they're in multi-tenant running in parallel, such as crosstalk, or across the users in time if you abuse something like a reset gate. So these are the main categories. So a little shorter today. So I think that that wraps up the what I want to talk about, the crosstalk and fault injection across the qubits in a multi-tenant setting, and then this fault injection across reset gates in this interleaved setting. These are the main things. Cool. So so next week we'll continue discussion of some other topics, and then I will hopefully get into the projects and the student presentation. So so thanks so much, and